Okay, so we have 4 problems here. We'll start with the first one. Okay, so we have 2 particles that are separated by a half meter that were rubbed together. Okay, they were both neutrally charged before the rubbing. And then we have 4.20 times 10 to the 9th power number of electrons moved from one particle to the other particle. So what is the charge between them? No, that's a typo. What is the force between them? Okay. So let's identify some piece of information here. Yeah, we'll keep it orange. They're separated by a half a meter. It's going to be our radius. Okay, so 4.20 times 10 to the 9th power electrons. That's going to be n number of electrons that moved over. And we're looking for the force. Okay, that's pretty much the only information we're given here, which is not much to work with. However, okay, Viking level kids, we are not doing this. Okay, this is pretty much only being covered with AP. Okay, so AP kids, okay, we should know that Q, which is the charge, is going to equal the elementary charge of a single proton or electron multiplied by the number of then protons or electrons. Okay, so in this case, if we had 4.20 times 10 to the 9th number of electrons move over, we could figure out the charge then. So the charge is going to be our elementary charge, which in this case, if you notice, electrons are going to be a negative 1.60 times 10 to the why am I blanking on this? Negative 19th power times the 4.20 times 10 to the 9th number of electrons. Okay, now this number, okay, these two are going to give us the total charge on that, right? So if each electron carries a charge of 1.6 times 10 to the negative 19th power, okay, and there's 4.20 times 10 to the 9th, or would that be 4.2 billion electrons moved over, each of them carrying the charge of 1.6 times 10 to the negative 19th. That's going to give us then the total charge, okay, on this object. Okay, so let me get my calculator. We have 1.6 times 10 to the negative 19th multiplied by 4.2 times 10 to the 9th. And we got have 6.72 times 10 to the negative 10th Coulomb. Okay, the other way to write it, okay, 0.672 nanocoulombs. So either way, it's the same thing. Again, just kind of using that metric system to write. So now, I made a slight mistake. Again, this number technically should be negative because, again, the charge is for the electrons that moved over. So let's draw 2 particles here. We'll have a red particle because one particle is going to end up being positive, and then negative will be green. Okay, Christmas colors. So we'll go, this is negative. We'll do red as positive. Other information we know about these two, they are 0.5 meters apart. Okay. So the charge on the negative one, okay, because we had electrons move from here to there. Okay, so the charge on the green is going to be a negative 6.72 times 10 minus 10. Okay? However, the charge on the positive then is going to be positive 6.72 times 10 to the 10th. Okay? The reason being, if they were neutrally charged beforehand, okay, and one object is going to lose the electrons to the other, they're going to have equal but opposite charges. Okay? Law of conservation of charge is at work here. Okay? You can't create or destroy imbalanced charges. So if we're going to transfer charge and there was a net charge of 0, okay, before, afterwards there still is a net charge of 0. Okay, we're going to assume this system is isolated here. Okay. So now we know the charges. Okay, we know our K, which is our constant. Let me write that over here. So K being our constant. And the constant, we're going to use 9.0 times 10 to the 9th. Technically, it's like 8.9987 something to the 9th power. I just round to use 9. So once we have all of our information, we're going to plug it in. The electrostatic force, okay, is equal to K Q1 Q2 R squared. Plug in our information now. 9.0 times 10 to the 9th. Negative 6.72 times 10 to the minus 10th. And then positive 6.72 times 10 to the negative 10th. Oops. This is divided by, not r, but 0.5 squared. So there, now we have the electrostatic force. It's going to equal, let me do some number crunching real quick, 9 times 10 to the 9th times 6.72 to the negative 10th, giving us 6.048. Multiply that by 6.72 times 10 to the negative 10th again, giving us a long decimal. Divide that by 0.5 squared. And the electrostatic force, 1, 2, 3, 4, 5, 6, 7, 8. I have is 1.63 times 10 to the negative 8th newtons. Let me double check that. Let's see, 1.3. Yes, 8 decimal places. Okay. So the electrostatic force between those is going to be 1.63 times 10 to the negative 8th newtons. Okay, so a little quick review of this problem. Okay. Use gold. Okay, so we took the number of electrons that moved over, multiplied by their elementary charge, okay, in order to find the charge. Once we were able to do that, we plugged that in to here. Okay, that's where our charges are going to go. Again, the drawing illustrated kind of law of conservation of charge. If there's a net charge of 0 beforehand, if they're both neutrally charged, and then afterwards electrons move from one to the other, okay, then that's conservation of charge. Okay, the net charge after still has to be 0. Okay, which you can see a positive 6.72 and a negative 6.72 are going to be a net of 0. Okay, then we simply plug in our information into the equation and solve straight up. All right, let's move on to number 2. Number 2, two metal plates are negatively charged with 720 nanocoulombs. How far do they need to be separated to achieve a force of 100 newtons? So let's go through and highlight our information. They're both negatively charged. We have the charge amount. Okay, how far? That's what we're looking for. Okay, and then we know the force. write this out for you guys. So Q, oops. Q1, Q2. Actually, they should be both negative. Okay, so we know both charges. We know the force is 100. And we know K is 9 times 10 to the 9th. Okay? Let's do the equation blue here so you can see the red cancellations. So again, now it's pretty simple. Okay? We don't really have to do anything except algebra and manipulate our equation to get what we want. Don't even need a substitute. Okay? So what we're looking for is r squared. We need to get r by itself because that's what we're looking for. We're looking for the distance. Okay? So right now we see r is at the bottom of the fraction. So we're going to multiply by r here on both sides. R squared, my fault. We're going to multiply by r squared on both sides. Okay, on the right-hand side, they're going to cancel. Okay, and on the left-hand side, they're going to remain just f r squared times the electrostatic force. That's going to be K Q1 Q2. Okay? Now again, we're working to get r by itself, and we notice that still, okay, the electrostatic force is now attached to it. So we're going to divide because they're being multiplied together. Remember that r squared right here, those two are being multiplied. So we're going to divide, okay? The electrostatic force divided by the electrostatic force is 1, so they'll cancel. And the left-hand side, leaving us r squared equals K Q1 Q2 over the electrostatic force. Okay? We're going to move this on up over here. Okay. R squared I'm just going to write F. Oop. Okay. The last thing, R technically is still not alone. Okay, we have that square, so we're going to square root that, and we have to square root both sides. Okay, what's going to happen on the left-hand side is the square root and the square are going to cancel, which is going to give us R by itself. Okay, so now we have R equals the square root of K Q1 Q2 over the force. Okay, so that was some algebra there just to kind of show how we're going to cancel and manipulate our equation. Now we have the equation set up how we want. All we have to do is plug in our information. Now, let's say that you started from step 1 here. Let's say from here you want to plug in all your information. So each Q you put 720, negative 720 nanocoulombs. The force on the left-hand side you just plug in 100. K is 9 times 10 to the 9th. You can do it with numbers and then do the same exact steps that I did, just using the numbers. Okay, I leave the numbers out until the end. Okay, but whichever you prefer is fine. R 10 to the 9th. And they're both negative 720 nanocoulombs. And we're going to divide that by 100. Okay. Now, what I should touch on here is the 720 nanocoulombs. Okay, again, a nanocoulomb equals times 10 to the negative 9th coulomb. Okay, so essentially if you take this number, the negative 720, and move the decimal left 9 places, that is the number in coulombs, and that's the number you should enter in your calculator, not 720. Okay, so R equals, we'll multiply the top just so make sure you guys don't type in the wrong number. 9 times 10 to the 9th, okay, or 9 billion, times 720 times 10 to the negative 9th, times 720 times 10 to the negative 9th. We get 0.00467 divided by 100. Oops. Radius equals square root of 0.00467. Square root of that. Radius equals 0.068, and this answer is in meters. Okay, so let's review that real quick. We have our given information highlighted in orange. Okay, they're written out in the black on the left. The nanocoulomb, again, refers to times 10 to the negative 9th power, number of coulombs, okay? And then we simply just had to do algebra to get R by itself, or manipulate the equation, okay, to get R by itself. Now, in this video, I did it without the numbers, okay? I simply moved the variables. If you first wanted to plug in the numbers and then manipulate the equation with numbers, that's also fine. You would do the same exact steps as I did, and should have the same exact number answer as well. Okay? Moving on to number 3. Okay, a proton is put near a particle that is charged. Again, let's highlight our information so we know a proton. Okay, we know a lot of information just from hearing that. Okay, we know they're separated, so meter, again, indicates distance, and in this case, that'll be our R. Creating a force, okay, a couple things about that force number we could talk about, and then we're looking for the charge of the other particle. Okay, so let's do a little drawing here. So proton's going to be, we're going to say that's red, because proton's going to be positive. So you have a proton there. Okay, and it's a positive charge. They're separated by a certain distance, creating a force of negative 4.5 times 10 to the negative 20th power. Now, the force is negative, which means it has to be an attractive force. Now, if there's a proton, the only thing that will attract to a proton is a negative force, or a negative charge, I should say. Oh, I'm not going to use blue. Let's use green. Keep going with green. So there has to be something that's negatively charged over here. Okay, that distance is the R, and that's where is it? It's 3.4 times 10 to the minus 4. 3.4 times 10 to the minus 4th. All right, that gives you a little visual of what's happening right now, and we know the force between them. Okay, the force is right above that picture. So I'll go ahead and write all of the information out. So F equals negative 4.5 times 10 to the negative 20th power. R 3.4 times 10 to the minus 4. Now Q2 is what we're looking for. What's Q1 going to be? What is Q1 going to be? And we also know the constant. Now, Q1, okay, again, we talked about it. It's a single proton. Okay, so we also said that the charge is going to be the elementary charge times the number. Right now, obviously the charge for a single proton is its elementary charge, right? It's 1.6 times 10 to the minus 19th, okay, times 1. So Q1, 1.6 times 10 to the negative 19th power. Ta-da! Okay, so that's our Q1. Again, it's a charge of a single proton. And again, it's positive because proton is a positive charge. Now, we are looking for Q2. So same exact thing as we did last problem. So this is just going to require some algebra. The electrostatic force, K, Q1, Q2 over R squared. Okay, we are looking for that guy. First step we should do is to get rid of this fraction. So let's multiply by R squared on both sides. R squared on the right cancels, leaving us with R squared, electrostatic force, K, Q1, Q2. All right. Now, again, we're trying to get this guy alone, which is being multiplied by Q1 and K. So we could divide by K and Q1. Okay. On the right side, they're going to cancel. We're going to send this back up top. Oh, keep going. We're going to send this back up to the top. So now we have R squared electrostatic force is being divided by K, Q1. That equals Q2. Okay? So far, so good. Now we have our equation, how we want it set up. All we have to do is plug in the information. The radius is 3.4 times 10 to the minus 4th power. So 1, 2, 3, 3, 4 multiplied by negative 4.5 times 10 to the minus 20th. Eek. K, and Q1 is simply the elementary charge. That's going to be divided by 9 times 10 to the 9th. That's being multiplied by 1.6 times 10 to the negative 19th. Now, let's take a quick look here. Let's see if this is going to make sense for us. So we stated earlier that based off of this unknown charge here has to be a negative because it's an attractive force, okay, which means Q2 has to be negative. At the top, we only have one negative number. At the bottom, we have no negative numbers, indicating that this number will be negative. Okay, so we are on the right track. Let me get out my calculator. So we have, let me take this in, 0.00034 times 4.5 times 10 to the negative 20th. We have 1.5, oh boy. That's going to be divided by 9 times 10 to the 9th, or 9 billion times 1.6 times 10 to the negative 19th. Which gives us 1.44 times 10 negative 9th. This is going to be Q2. Okay. .53 times 10 to the negative 23rd. Divide that by 10 to the negative 9th. We get a charge of 1.03 or 1.063 times 10 to the negative 14th. Now, okay, so again, both levels should be able to do this. We have simply given our information. In the blue, again, we are just arranging the equation in order to get Q2 by itself. Now, Viking level kids, I understand I have not shown you this equation, Q equals En, and that's fine. Okay, you should still be able to solve this problem because it specifically tells you that it's a proton. And you need to know that a proton, okay, or a single electron, the elementary charge, okay, is the charge for a single proton or electron. Okay. Then we simply, in the blue, we rearrange the equation, we plug in the equation, and we solve. Now, AP guys, on the AP test, they may ask you, does this charge make sense? Or can this charge be plausible? Okay. Now, how do you think we could ensure that this charge is possible? Okay, we're gonna revisit that equation that I just highlighted. Q equals En. Okay. So if we take Q and we divide it by E, that'll equal the number protons or electrons. Now, we can't have a decimal, can we? We shouldn't. It should be a whole number, right? Because if you take the charge by the elementary charge, it should give us a whole number, right? We should only have whole either protons or electrons. So let's test this out. And again, okay, I made these numbers up on a whim, so I don't know if this charge is realistic or plausible quite yet. Okay, so this is times 10 to the negative 14th. So 1.063 times 10 to the 14th, that's negative. That's going to be divided by 1.063. Divided by 1.6 times 10 to the 19th negative. Okay. So, the number I got was 66,437.5, which means that charge is not possible. Okay, because it's telling us that's the charge of 66,437 and a half, what would that be? Electrons. Again, I just caught my mistake. I don't know if you're following. Apologize. Yes, I highlighted Q2 should be negative. This should be negative. Therefore, this should be negative. Okay. So we have both those charges negative, yes, and then also that's the charge and the charge of an elementary charge of an electron. The negative divided by a negative should give us a positive number. Now, let's say, AP guys, this number was just 66,437 on the dot. Okay, then that charge is possible, okay, because that number is a whole number. Okay, that would work. But in this case, we got that 0.5, so it is not a possible charge, okay? So that's something that you'll need for the AP test and possibly on the test on Monday. All right, and let's move on to our very last question. Okay, there's a force between two charged objects of 17 newtons, and they're 0.2 meters apart. If the charge for one object is 850 nanocoulombs, how many excess protons or electrons does the other charge have? Okay, now there's a few things to this, so let's take a dive in and let's look. So we have the force, Newton's gives it away. We have the distance, okay. We have the charge of 1, okay, this is a positive charge. The charge for the other ones, okay, is what we're looking for. Okay, the other charge. Now notice, okay, some things we can tell about this. I'll just write some of the information down first. So force is going to be 17. The radius is 0.20. Charge of 1, 850 nanocoulombs, or 850 times 10 to the negative 9th. Okay, we don't know charge 2. Okay, now charge 2 will lead us to n. Again, n is the number of excess protons or electrons. Now look at the force. The force is a positive number. It's positive 17, which must mean that it's a repulsion force. If the charge of the first object is a positive 850 nanocoulombs, indicates that it's a positive charge. In order for a positive charge to have a repulsion force, the other charge needs to be a positive charge as well. Okay, so we know that the other charge is going to be a positive charge, and if it's a positive charge, it's going to have an excess amount of protons compared to its electrons. Okay, so let's begin. We have the force. Electrostatic force is equal to K, Q1, Q2, divided by R squared. Again, I'll go through the algebra and how to cancel and get the equation that we want. That side's going to cancel. We have R squared times F, K, Q1, Q2. Divide by K. Oops. Let's do it in red. Divide by K, Q1. Bam, bam. Cancels. They move to the left. R squared F K Q1 equals Q2. All right. There's the algebra. We have our equation set up. All we have to do is plug in our information. So 0.2 squared times 17. Divide that by K is times 10 to the 9th. And 850 times 10 to the negative 9th. Okay, this is going to equal Q2. Bring this sun up over here. We have 0.2. We're going to square that. We're going to multiply it by 17. Divide that to 0.68. By 9 times 10 to the 9th times 7,650. All right, equals Q2 0.68 divided by Okay, so we have a charge of 0.000089 coulombs for charge 2. Charge 2 is significantly bigger than charge 1. All right. We got our first part. I'll highlight that in pink. We got our first part completed. We have found the charge that's on Q2. Now, knowing the charge is going to allow us to figure out how many excess protons or electrons we have. Okay, again, we said this is protons. What color should I use? Like this purple. Dark purple. Okay, we have Q equals En. Q divided by E equals N. Q being a 0.12348 N. Divide that by its elementary charge of 1.6 times 10 to the negative 19th equals N. Divided by 1.6 times 10 to the negative 19th. Ah, perfect. We have a whole number. Okay. We have 556,250. Okay, or all right. Okay, so here we do have a whole number, which means that charge is legitimate. Okay. So here we do have a whole number of excess protons. So again, that's just to clarify in case the problem asks you to do so. So review quickly on number 4. We have our information listed to the left. In the blue, it's simply rearranging the equation to find the charge. Once we know the charge, we can use the knowledge of the charge and the elementary charge to find the number of excess protons or electrons. Again, I do want to highlight the N is simply the number of excess protons or electrons on an object. It does not tell you the total amount, okay? Unless the object or a particle is completely void of another charge. So let's say that it has a charge of 1 Coulomb. Okay, it's a positive charge, which means it has a lot of excess protons. If it has 0, electrons, very, very unlikely. If it has absolutely 0 electrons, then the excess number of protons would be the total number of protons on that particle or element. Besides that, it's going to be too difficult to tell exactly how many, in our cases, total number of protons or electrons are on an object. We're only going to be determining the excess amount. Okay? So there we have it, the 4 problems. I'm going to post this video onto YouTube. I'll copy that link onto Google Classroom for you guys. And then I'm also going to post this note as well for you guys to look through the math. All right? Enjoy your guys' weekend. I'll see you Monday for the test.